Dear students, in the previous lecture, we studied about the spontaneous processes and entropy. Entropy, the disorderness of the system. We also studied about the second law of thermodynamics. The spontaneous processes which have the urge to take place of their own. We studied about two driving forces, that is decrease in enthalpy and increase in entropy. Through many examples, we studied that decrease in enthalpy or increase in entropy alone cannot be the deciding factor for a process to be spontaneous. The total entropy of the system should be greater than 0 for a system to be or the process to be spontaneous. There is another thermodynamic parameter, that is Gibbs energy, that correlates enthalpy and entropy, and how the value of enthalpy decides that whether the process will be spontaneous, non-spontaneous or at equilibrium. Let's see. Mathematically, entropy is equals to Q upon T, where Q is the heat absorbed and T is the temperature at which the heat is absorbed. The second law of thermodynamics says that during any process, the change in entropy of the universe is equals to the change in entropy of the system plus the change in entropy of the surroundings, and it should be greater than equals to 0. If a system loses heat, then the surroundings gains the heat and the entropy of the surrounding increases. Delta S surroundings is equals to minus Q system upon T. Heat that flows into or out of the system also changes the entropy of the surroundings. Entropy changes in surroundings. Heat that flows into or out of the system also changes the entropy of the surroundings. For an isothermal process, entropy change of the surroundings is equals to minus Q system upon T, and at constant pressure, Q system is simply delta H for the system. Delta S surroundings is equals to minus Q system upon T or minus delta H upon T. Another thermodynamic function, Gibbs free energy, denoted by capital G, that correlates entropy and enthalpy as delta G is equals to delta H of system minus T delta system, where delta H is the change in enthalpy, T is temperature and delta S is the change in entropy. Gibbs energy is also a state function. That is, it depends upon the initial and the final state of the system and not on the path by which that change has been achieved. It is also an extensive property. It depends upon the amount of the matter or the quantity of the matter contained in the system. We have earlier studied that for a spontaneous process, delta S should be greater than 0. But for a spontaneous process, Gibbs energy delta G should be less than 0. That is, its value should be negative. Delta G is easier to determine than delta S of the universe. So, we use delta G to decide that whether the process will be spontaneous or non-spontaneous. For a process to be spontaneous, delta G should be less than 0. If the value of delta G is more than 0, the process is non-spontaneous. And if the value of delta G is equals to 0, then the process is at equilibrium. Standard free energy changes. Standard free energies of formation delta G naught F are analogous to standard enthalpies of formation delta H naught F. Delta G naught F can be calculated as the total free energy of the reactants minus total free energy of the products. We can also find delta G as by knowing the values of delta H and delta S. We have to put the numerical values with their sign, the decrease or increase in the enthalpy or entropy. The equation delta G is equals to delta H minus T delta S shows that delta G changes with temperature. From the table, now we will see that how the sign of enthalpy and entropy will affect delta G, and then the value of delta G, that whether it is negative, positive or equals to 0, will decide the process to be spontaneous, non-spontaneous or equilibrium. Let's see one by one. If the value of delta H is negative and delta S is positive, then putting these values in the equation delta G is equals to delta H minus T delta S, the process is spontaneous at all the temperatures. In the second case, when the change in enthalpy is positive, change in entropy is negative, then the delta G value comes out to be positive at all the temperatures, and hence the process will be non-spontaneous. Let me remind you once again, if the value of delta G is negative, the process will be spontaneous, but if the value of delta G is positive, the process will be non-spontaneous. Let's see the third case. If delta H is negative and delta S is also negative, then the process is spontaneous at low temperature but non-spontaneous at high temperature because the sum total should be negative. The fourth case, delta H is positive and delta S is also positive. Then it is spontaneous at high temperature and non-spontaneous at low temperature. So by knowing the sign of entropy and enthalpy change, we can find out the sign of delta G. There are many reactions for which delta G is positive and the process is non-spontaneous. For example, in the case of the blast furnace, when we extract iron from the hematite or the magnetite ore, the process is non-spontaneous. In such cases, to make it spontaneous, we couple it with the process which is very highly spontaneous. Then, by coupling of the two reactions, the overall delta G becomes negative and the process automatically becomes spontaneous. This is the practical utility of this equation, the Gibbs equation. Third law of thermodynamics. Absolute zero is a state of zero motion. This means absolutely no entropy, and that cannot be reached. The state of zero entropy cannot be reached. Third law of thermodynamics states that the entropy of a perfect crystalline substance is zero at the absolute zero of temperature. From the figure you can see that as we are moving from solid to liquid and liquid to the gaseous state at melting and the boiling temperatures respectively, the entropy is increasing, and in the reverse order from gas to liquid and liquid to the solid state, we can see that the orderness is increasing. The solids are more ordered as compared to the liquid, and liquids are more ordered as compared to the gaseous state. Entropy increases when there is a change of state. The solids have the lowest entropy and the gases have the highest entropy. Dear students, in this unit thermodynamics, we study about the internal energy which is associated with every fixed quantity of a substance and which is a sum total of many different energies which the constituent particles of the system possess. To find out the exact value of internal energy is not possible, so we find out the change in the internal energy. The another thermodynamic parameter we studied is about the enthalpy or the heat content of the system. Just like internal energy, to find the exact value of enthalpy is also not possible. And delta H, that is enthalpy, and delta U, that is internal energy, are related by the equation delta H is equals to delta U plus P delta V. We also studied about enthalpy of the phase transformations and different types of reactions. We studied that there are ionic solids and there is a lattice enthalpy, and to find out the lattice enthalpy of the ionic solid directly or experimentally is not possible, so we use Born-Haber cycle to find it indirectly. Then there are naturally occurring processes which are spontaneous, they have urge to take place of their own, and the driving forces behind a spontaneous process. Entropy, the randomness, the messiness of the system, which is one of the important driving force for a process to be spontaneous. Last, the Gibbs energy that correlates enthalpy and entropy by the equation delta G is equals to delta H minus T delta S. For any process to be spontaneous, delta G should be less than 0. It should be a negative magnitude. If it is more than 0 or positive value, the process is non-spontaneous. And if delta G is equals to 0, the process is at equilibrium. We also studied about first, second and third law of thermodynamics. Thank you.